Finding the limit of f of x as x approaches 2, where f is defined as 1 at all values x does not equal 2, and 0 at x equals 2. Because f of x equals 1 for all x other than x equals 2, you can conclude that the limit is 1, as shown below. So you can write the limit as x approaches 2 of f of x equals 1. The fact that f of 2 equals 0 has no bearing on the existence or value of the limit as x approaches 2. For instance, if the function were defined as f of x equals 1 at x does not equal 2, and 2 at x equals 2, the limit would be the same. When limits do not exist. The first example of a limit that fails to exist is behavior that differs from the right and left. The first example is the limit of as x approaches 0 of the absolute value of x over x. Looking at the graph of this function, you can see that for positive x values, this yields 1, which is greater than 0, and negative x values yield negative 1, which is less than 0. This means that no matter how close x gets to 0, there will be both positive and negative x values that yield f of x equals 1 and f of x equals negative 1. Therefore, we can conclude that this limit does not exist. The next example of a limit that fails to exist is unbounded behavior. Looking at the limit as x approaches 0 of 1 over x squared, we can see that from both the left and right side, the limit will be approaching infinity, and therefore we can conclude that the limit does not exist. The third example of a limit that fails to exist is oscillating behavior. Looking at the limit as x approaches 0 of sine of 1 over x, we can see that no matter how small the window is, this function will always oscillate between 1 and negative 1, so it is impossible to determine one limit, therefore the limit does not exist. The formal definition of a limit is, as x approaches some number c, the function f of x will become closer and closer to another number L. Theorem 1.1 states that allowing b and c to be real numbers and m to be a positive integer, if the function f of x equals b, the limit as x approaches any number c of this function will be b. If the function is f of x equals x, the limit as x approaches c will always equal c. And if the function is f of x equals x to the nth power, the limit as x approaches c will equal c to the nth power. To find the limit of a polynomial, such as the limit as x approaches 2 of 4x squared plus 3, all you have to do is plug in the number and then simplify. Two special trigonometric limits that are worth knowing is the limit as x approaches 0 of sine of x over x equals 1, and the limit as x approaches 0 of 1 minus cosine x over x equals 0. To look at an example of a limit involving a trig function, we can look at the limit as x approaches 0 of tan of x over x. Since this is indeterminate, we have to then change the function to sine of x over x times 1 over cosine x. And due to our special trig limit, we know that the sine of x over x as the limit of x approaches 0 is 1, and we can then plug 0 into 1 over cosine x. We see that the limit of as x approaches 0 is 1 times 1, or just 1. The definition of continuity is f of c is defined, the limit as x approaches c of f of x exists, and the limit as x approaches c of f of x equals f of c. Then the function f of x is continuous. Looking at these three examples, we can see that all three have discontinuities at a point c, and two of them are removable. One-sided limits, for example the limit from the right, means that x approaches c from values greater than c, and this is denoted as the limit as x approaches c plus. Similarly, the limit from the left means that x approaches c from values less than c, and this is denoted as the limit as x approaches c minus. The definition of continuity on a closed interval is f of x is continuous on the closed interval a, b, if it's continuous on the open interval a, b, and the limit as x approaches a from the right of f of x equals f of a, and the limit as x approaches b from the left of f of x equals f of b. An example of a one-sided limit is the limit as x approaches negative 2 from the right of the square root of 4 minus x squared. Looking at the graph, we can determine that the limit of f of x as it approaches negative 2 from the right is 0. The continuity of a composite function. If g is continuous at c and f is continuous at g of c, then the composite function given by f of g of x is continuous at c. The intermediate value theorem states that if f is continuous on the closed interval ab and k is any number between f of a and f of b, then there is at least one number, c, in the closed interval ab such that f of c equals application of the intermediate value theorem. Looking at the function f of x equals x cubed plus 2x minus 1, we know that f of 0 is less than 0 and f of 1 is greater than 0. So there exists a value c in the closed interval 0 to 1 such that f of c equals 0. Looking at this graph, we can determine that the limit of f of x as x approaches c from the right, as well as the limit of f of x as x approaches c from the left, both approach infinity. Therefore, the limit of f of x as x approaches c is infinity. A vertical asymptote can be found at the x value that makes the denominator of a function equal 0. One example is f of x equals x squared plus 1 over x squared minus 1. By factoring the denominator, we can see that it also equals the quantity of x minus 1 times the quantity of x plus 1. And if we set both of those equal to 0, we can see that there's a vertical asymptote at both 1 and negative 1. Our second example is f of x equals the cotangent of x. We can then change this to cosine x over sine x. By setting the denominator equal to 0, we can see that there are vertical asymptotes at x equals 0, pi, 2 pi, and so on and so forth. One example of determining an infinite limit is looking at the function f of x equals x squared minus 3x over x minus 1. Because looking at the denominator, we can conclude that f of x has a vertical asymptote at x equals 1. This means that each of the given limits is either infinity or negative infinity. A graphing utility can be used to help determine the result. From the graph shown on the paper, you can see that the graph approaches infinity from the left of x equals 1 and approaches negative infinity from the right of x equals 1. So you can conclude that the limit of f of x as x approaches 1 from the left is infinity, and the limit of f of x as x approaches 1 from the right is negative infinity. Thank you, and the end.